Now it turns out that there's a very useful different way to calculate electric fields, which is to use the concept of voltage or electric potential. Here's the idea. If you remember, electric field is a vector, so it's like the green arrows in this diagram over here. At every point in space you've got an arrow showing the electric field. Now it turns out that for electric fields, not magnetic fields, only electric fields, you can define a scalar field, a field that's just numbers, not vectors, called electric potential. And the electric field is the gradient of the electric potential. So I've drawn that here. The electric potential is these contour lines, so the highest contour is red going down to blue ones, and the electric field is a slope. The way to think of this is electric potential is like height in the landscape, and electric field is like the slope. So if you imagine this as a contour map of a mountain, that's the summit of the mountain, there's a saddle and you're going downhill, then the height is the electric potential, and the slope, the gradient, is the electric field pointing downhill. So you might find that analogy useful. Now electric potential is measured in volts. It's also be called the voltage. So the potential difference between two places is just a difference in height between the two. What this means is that, technically speaking, the electric field is the gradient d voltage by d position. It's actually a vector one, and we'll do that in second year. What that means in practice is that over some small distance, the electric field is the change in the voltage, the potential, divided by the distance. So let's say we have two places here, and they're some distance d apart. Then the difference between the potential here and the potential here is this delta V. If you divide that by the distance, you get the electric field. That's just the electric field is gradient of slope. Or equivalently, the potential difference, the change in voltage between two places, is E times D. That's just saying that, in the analogy, the change in height is equal to the slope times the distance. So if you've got a 1 in 20 slope and you go 1 meter, or 20 meters, you've gone up 1 meter.